When an element reacts with another element, one of the ways that they can bond together is to form bonds that result from sharing the electrons that are in their valence shell. This happens when elements have nearly complete valence shells because neither one of those elements would want to give up an electron because they're both trying to complete their shell. And we're looking then at probably the nonmetals, the ones that are nearly full. So instead of either one having to give, they both just allow their electrons to be shared between them. That's when we have a covalent bond. A covalent bond resulting from a shared pair of electrons in a pair of atoms is called covalent because the prefix co means partner. And of course, if you look at the ending of the word covalent, valent comes from valence and the valence electrons. So the nonmetals, carbon, nitrogen, oxygen, fluorine, the ones in the upper right-hand corner of the periodic table are the ones that have nearly full valence shells. Remember, carbon's group has 4 valence electrons, nitrogen's group has 5 valence electrons, oxygen's 6, and fluorine and the other halogens all have 7. So they're very close to having a full valence shell. Remember, 8 is sort of the magic number everybody's looking for. And being that close means that none of them want to give away their electrons. If they share their electrons, neither one of them has to. So what happens is the shared electrons are in the valence shells that overlap as these atoms come together. And those electrons then are attracted to both nuclei because of the positive charge in the nucleus. And remember that the nucleus has a positive charge because it is made up of protons. If this covalent bond forms, when we show it on paper, the easiest way to show it is to just represent that shared pair of electrons by drawing a line between the two atoms. So iodine forms covalent bonds with itself. Iodine is one of the diatomics, and it then looks like this with 2 letter I's and a dash or a line between them to represent that bond or that shared pair of electrons. So if we take a look at the Y behind it, if we look at hydrogen here in the top row, you can see that hydrogen each has 1 valence electron. If those two atoms come together and their valence shells overlap, then it's as if each of them has 2 electrons in their valence shell. Now that's not 8. I do understand 2 and 8 are very different numbers, but remember that the first energy level is actually full with 2 electrons. So by doing this, the 2 hydrogen atoms now appear to each have the 2 valence electrons they want to fill their shell. You can see the same thing happens when fluorine atoms form their diatomic molecule, except that each fluorine atom has 7 valence electrons. So would really like to have one more to get their complete shell of 8. So when they overlap, that shared pair of electrons makes each of them appear to have 8 in their valence shell. And that, of course, would make them happy. Taking a look at combining something other than the diatomic, if 2 oxygen atoms combine with a carbon atom, this can complete the valence shell for each of them as well. But this one's a little trickier because carbon has only 4 and oxygen only has 6. In order to get to 8, of course, that means oxygen needs 2 more. Well, it's going to borrow 2 from carbon. That would, before the next oxygen atom combines, give carbon only 6 valence electrons. And since that's not enough, we need another oxygen atom to donate 2 more electrons. So carbon is benefiting and getting its valence shell full with 8, but it needs to borrow and share 4 extra electrons to make that happen. But each oxygen atom at 6 only needs to share 2 of carbon's valence electrons. So it would look something like this over here. Taking a look at this last example, since carbon needs to have 4 extra electrons that it doesn't have, and each fluorine atom only needs to have 1 more, it actually requires 4 fluorine for every 1 carbon in order for everybody to have their valence shells full. And you can see that's what happens here. Each fluorine allows 1 of its valence electrons to be shared with carbon. Carbon then benefits and has the 4 that it needs, and each fluorine has the 1 extra that they need. So there would actually be 4 covalent bonds in order for a carbon atom to be complete. So how are things going to bond? How many bonds are going to form is always going to depend on how many electrons are needed in order for it to fill its valence shell. So as you saw in those last examples, each one needs to have enough bonds to complete their valence shells. So group 16 with their 6 valence electrons will usually form 2 covalent bonds to pick up the 2 electrons they need. Group 15 with 5 valence electrons, they're going to form 3 bonds because they need 3 extra electrons. And group 14, the carbon group with only 4 valence electrons, they're going to always have to bond 4 times in order to pick up the electrons that they are needing. When covalent bonds form, the new compound that has formed then becomes called a covalent compound. What's interesting about these guys is that each of these little groups actually is able to exist as individual molecules. The way that they bond together, as you began to see in some of those diagrams, gives those molecules a specific shape. And these things that have a specific three-dimensional shape then also have certain properties because of those shapes. One of the things that is very true of most covalent compounds is that they have very low melting and boiling points. In fact, many covalent compounds are gases at room temperature. Some of them are liquids and some of them are solids. But if they are liquids at room temperature, they have a low boiling point. And if they are solids at room temperature, they often have a very low melting point. I think of wax, like the wax that makes up a candle. It doesn't take very much energy in order for wax to melt. Low melting point and boiling points are the result of weak bonds. Covalent bonds, because of the way they attract the atoms to each other, means that the molecules that are made are not very attracted to each other. And that's why they have very low melting and boiling points. It does not take very much energy to separate those molecules from each other. They also have no charged particles, so that means they are not conductors of electricity. When electrons are shared, sometimes those electrons are shared very evenly between the nuclei of the atoms that are sharing them. When that happens, we call them nonpolar covalent bonds. The ones that are the most likely to share equally are the ones that are the same. So the diatomics, the halogens and oxygen, nitrogen, and hydrogen, the ones that share their own electrons are actually the ones that are going to share their electrons very, very equally. And so that means their bonds would be nonpolar covalent bonds. So our 7 diatomics, hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, actually exist in nature in pairs to make the element more stable. And when they share their electrons equally. But when atoms share electrons and they're not playing nice, they're not sharing equally, then we have something called a polar covalent bond. Because one atom is usually a little bigger, a little stronger, has a little more pull on the electrons then spend more time with that atom than they do with the other atom in the bond. That makes it slightly negative on that side of the molecule and leaves the other side of the molecule slightly positive. We can use little symbols called delta symbols, Greek letter delta, with a positive or a delta with a negative to show which sides are slightly positive and slightly negative, because the Greek letter delta means partial. Water molecules do this. Water molecules don't share their electrons equally. The oxygen is much, much larger and stronger, and so pulls more on the shared electrons than each hydrogen atom is able to pull. That means those electrons spend more time next to the oxygen and less time by the hydrogen, leaving the oxygen slightly negative, so it has the delta negative, and each hydrogen atom with a slight positive charge, because it's almost as if they have lost their electron and become a positive ion, but not quite, so we label them with the delta positive.